All right, welcome back, everybody. In this video, we'll be finishing up section 10.1 by working on ellipses still. And in this first example, we're going to be doing an application problem. So here's the story. It says an arch has the shape of a semi-ellipse, that is half of an ellipse. In this case, it's the top half. The arch has a height of 8 feet and a span of 20 feet. Based on this, we want to find an equation for the ellipse and then use that to find the height to the nearest hundredth of a foot of the arch at a distance 4 feet from its center. So what would be good to do is probably start with making a little picture of what this arch is going to look like. So let's do that. So all right, so there's our arch. And we're going to want to make an equation out of this, so we should actually put it onto a coordinate system. So let's do that, actually. So let's see, there's our grid. So I don't want that one though. So okay. All right, so that's okay. All right, so it says the arch has a height of 8 feet. So I know that the kind of top of it is going to be 8, and the span is 20 feet. So that has to be at the point 10, 0, and this would have to be at the point negative 10, 0. I don't need the bottom half of the ellipse, but if you want, we can draw it in. So from here, we're to come up with the equation for the ellipse, and then I'll answer the rest of the question after we've got that done. So this thing is pretty clear that it's wider than it is tall. So it's x squared plus y squared. We need to figure out the denominators, set equal to 1. Okay, so the distance from the center to one of the vertices is 10. And so 10 squared is 100. That's in the x direction, it's bigger. So denominator on the x term is going to be 100. And then for y's, I don't have that yet. So in the y direction, the distance from the center is to the covertex is 8. And so 8 squared is 64. That'll be the denominator for the other one. So there's our equation for our circle, or our ellipse rather. And so now we want to find the height to the nearest hundredth of a foot, a distance 4 feet from the center. So take that over a little bit further. All right, so if you were to go a distance 4 feet from the center of that arch, we want to know that height. I'm going to call that h. Okay, so that's relatively straightforward. So basically we want to know, okay, when x is 4, what is the corresponding y coordinate going to be? So we're just going to substitute that into this equation, and then we'll find out. So when x is 4, okay, and so that's a 4. Looks kind of y-like. Okay. All right, so then we need to solve this thing for y. So let me multiply both sides by 6,400. Okay, we're going to work on getting the y part isolated, and then we'll end up taking the square root. Okay, so 16 times 64 is 1,024. And then that's going to be 100 y squared. All right, 5376. All right, so going through the calculations. So that looks like about 7.3. So to the nearest hundredth of a foot, so 7.33 feet. All right, so how we approach this, that's done. How we approach the problem was by drawing a sketch and locating our ellipse in this case so that it was centered at the origin, because we might as well, and that makes most sense. It's the easiest. We labeled the dimensions on here that we had, and from there we came up with the equation for the ellipse, and then from there we were able to answer the question. All right, so far our ellipses have been centered at the origin. Of course, they don't always have to be that way, and so we want to see how that works when they're not. And this kind of general guidance is going to apply for when we work on hyperbolas and parabolas as well. So if h and k, we continue using h and k throughout. If they're positive numbers, then replacing x by x minus h or x plus h, and replacing y by y minus k or y plus k has the following effects on the graph. Okay, x replaced by x minus h shifts it right by h units. X replaced by x plus h will shift it left by h units. Okay, and so we've seen that kind of thing happening in the past. So when we had, well, for one thing, we could consider the just a formula for a parabola, right? If you have y equals x plus 2 squared, we know that has been left shifted by 2 units. If we have y is x minus 3 squared, that will have been right shifted by 3 units. In the x direction, x plus 2 was a left shift, and then x minus 3 was a right shift. Okay, for y, if we replace y by y minus k, that will be an upshift by k units. Y by y plus k, that will be a downshift by k units. At first, that can seem like it's contrary to what we had before. Before we thought, okay, well, plus is up and minus is down. But notice that we're replacing the y's, right? And so take a look here. If you think about the graph of y equals x squared, we know that y equals x squared plus 3 would be a shift up, right? But if you take that plus 3 and put it on the y side, that is going to be a y minus 3, right? Similarly, y equals x squared minus 5, that would be a downshift by 5 units. If I put that minus 5 onto the y side, it'll be a y plus 5, okay? So the behavior there is kind of a lot more like we had seen for the horizontal in the past. So basically for the x and the y, it's almost kind of opposite of what your intuition might tell you. X minus h, a right shift by h, x plus h, a left shift by h. Y minus k is upshifted by k units, y plus k is downshifted by k units. Okay, so we'll try to keep that in mind as we find the equation of this ellipse. Okay, all right, so let's do that. So we want to find the equation of the ellipse. We know the vertices are at -1, -4, and -1, 6. So let's go ahead and draw those on first. So -1, -4, and -1, +6. All right, so those are the vertices, and so it's pretty clear that our ellipse is not centered at the origin anymore, right? When your ellipse is centered at the origin, the vertices lie along one of the coordinate axes, and here it does not. Okay, we also have the foci. The foci are at -1, -3, and -1, 5. Okay, notice that they're both 1 unit away from a vertex, and that has to happen. All right, so then what we probably should figure out is where the center is, okay? So the center will be halfway between the vertices, right? So taking a look at the two blue dots here, one is at -4, one is at 6. How far is it from -4 to 6? It is 10 units, right? So that means half that distance would be 5. So 5 units down from 6 would be 1. 5 units up from -4 will be 1. So the center has to be at -1, 1. Okay. All right, so next we're going to need to start building our equation. So we know that it's going to be x in parentheses, y in parentheses to be equal to 1. We'll have to know the two denominators. Okay, so we need to figure out the part in parentheses. So the center, you could think, okay, well, normally the way these have been, the center has been at the origin. So this one needs to be left shifted by 1 unit. Okay, so looking back at the table, a left shift by 1 unit, it should be x plus 1. Okay, it's been upshifted also by 1 unit. So we're replacing our y by y minus k. So if it's upshifted, that'll be y minus 1. Okay. All right, so there's our center. And then the rest of it is going to be relatively smooth sailing. So the distance from the center, this thing is taller than it is wide, right? The foci are on the major axis. So the distance from the center to a vertex is 5, right? And so that was from the center to a vertex is 5 units. So that means the denominator in the y direction is 5 squared or 25. Okay, and then to figure out the other denominator, we'll again use the equation c squared is a squared minus b squared to help us get that done. So the foci, the distance from the center to a focus is 4 units, right? So our c is 4. Okay, and so we'll use that to help us find our b squared. So 16 is equal to 25 minus b squared. And so b squared has to equal 9. Okay, so that will be our other denominator is 9. Okay, so that's our equation for our shifted ellipse. Okay, so we should have one more example. Okay, so for this one, we have one more ellipse to do. This time we need to sketch this thing, and you'll notice that it's kind of multiplied out like we saw with that one equation of a circle. So we're going to again need to do some completing the square to figure out what the kind of format for this ellipse is going to be, and then we'll go from there. Okay, so the first thing to do is I'm going to rewrite this so that all the x terms are together. So we'll have x squared plus 6x. Let me leave a little hole. We'll have 4y squareds minus 8y. And then let me put that plus 9 over to the other side as a minus 9. Okay. All right, so all I've done is physically move things around. I keep the x terms with the x terms and the y terms with the y terms. Okay, so now we're going to want to complete the square on this thing now, so let's do that. So for the x part, half of 6 is 3. 3 squared is 9, so let me add 9 to both sides. Okay, and so we'll do this in 2 steps. It's a little longer, so 2 steps is good. So the first 3 terms, x squared plus 6x plus 9, that will factor as x plus 3 squared. And then for the y part, you'll notice that the coefficient is a 4. So I'm going to factor that 4 out so that we'll just have y squared minus 2y. And that's still inside of parentheses. Our right side, negative 9 plus 9 is 0. So that'll change here in a second. Okay, so now really carefully, inside the parentheses here, y squared minus 2y plus what? Half of this 2 is 1. 1 squared is 1. I'm going to add in 1, okay? Drawing in this red plus 1, if we quit right now, this part would be 4y squared minus 8y plus 4, right? So that red 1 that I drew in is really increasing the right side by, or the left side by 4. So we're going to need to add 4 to the right side of the equation. Okay, so make sure that you understand that piece, what happened right here, because it can be really confusing. Why did he add 1 on one side and 4 on the other? Didn't really, okay? On the left side, I added 4. I drew in that 1 that is on the left, but if you quit and distributed that 4, you'd have 4 times 1 is 4. So drawing in this 1 right here, drawing in that 1 really increased the left side by 4. So to compensate, we're going to add 4 on the right side. Okay, I admit that takes a little getting used to, but you'll get some practice. Okay, so we'll have x plus 3 squared, we'll have 4 y minus 1 squared, and that's equal to 4. Okay, so we're getting there slowly. So now we need that right side equal to 1 again. So once again, we're going to divide all the way through by a 4. Okay, so that will have x plus 3 squared over 4 plus y minus 1 squared equals 1. All right, so there's finally our kind of standard form for our ellipse. And from there, we can read off where the center will be. Okay, the center's x coordinate will be -3. Its y coordinate will be +1. Okay. You want to remember that the kind of standard form for an ellipse looks like x minus h squared over, in this case, it's a squared, and then y minus k squared over b squared equals 1. Okay, so the center there is at hk. All right, so then our center at this thing is at -3, 1. And then we need to figure out all the rest of it. What are we supposed to do? Sketch the ellipse. Okay, easy enough. All right, so this thing is taller or wider? Okay, taking a look at the equation after we've rewritten it, the bigger denominator is on the x's, so that means it will be wider in the x direction. The square root of 4 is 2, so we'll go 2 to the right and 2 to the left of center. Okay, the other denominator was a 1. The square root of 1 is 1, and so we'll go up and down by 1 unit to create the covertices. Okay, all right, so there's the sketch of our ellipse. Okay, we weren't asked to do it, but I feel like finding the foci too, so let's go ahead and do that. It's a squared minus b squared, so that's 4 minus 1 or 3. Okay, so now we got to think about where those are going to be, right? Because they're going to have to be on the major axis, right? So c is equal to √3. So those foci are going to have to be somewhere on that major axis, right? So that means their y coordinate will be 1, and their x coordinate will be -3, that's the center, plus or minus √3. -3 plus or minus square root 3. Okay, that's the location of the foci. Okay, all right, so that takes care of this section finally. What we're going to do in the next section, which is on hyperbolas, is do something similar. We'll come up with the equation for hyperbolas or equations. We'll look at how to graph hyperbolas and how to create the equations given graphs or given information about the hyperbola. And then we'll do the same thing with parabolas. Okay, but that's it for right now. That finishes up section 10.1 for us. Let me know if you have any questions, and have a great day.